Okay, today is our great pleasure to have Dr. Yuta Kikuchi from Quantinuum. Yuta got his PhD from Kyoto University in 2018, and then he was a postdoc at RIKEN in both Japan and the Brookhaven National Lab. He joined Quantinuum in 2022 as a research scientist. And today he's going to tell us about something to prepare a thermal state using the Lindblad engineering. Yuta, the stage is yours.
Thank you very much for the invitation and a nice introduction. So today I will talk about Gibbs state prep, which is based on a collaboration with the colleagues at Quantinuum. Okay. So I don't think I need to introduce a lot, but just to set the stage, this is a Gibbs state that we're interested in. So the sigma beta is proportional to exponential minus beta h. And here h is the Hamiltonian of our interest, and beta is inverse temperature. And then, of course, there are many applications. I'm pretty sure that you are interested in studying a thermal state property of the quantum many-body systems. In a bit more algorithmic side, we have also applications in quantum machine learning model or optimization problem and so on. So if you can prepare this Gibbs state, we expect that this is very useful for other applications as well. From a bit different perspective, there's been also a lot of proposals to use this Gibbs state in order to achieve certain quantum advantage. For instance, there are several examples known about this Lindblad dynamics. So if you can simulate certain engineered Lindblad dynamics, then actually you can solve the BQP hard problem, meaning that it's believed to be classically hard, but quantumly you can solve. Or more recently, there have been an interesting proposal about the sampling problem. So you construct certain random Hamiltonians using what is called IQP circuit. And using that random Hamiltonian, you can construct Gibbs state again. And then you do some sampling task, and then that turns out to be classically hard, but classically you can do easily. So this is a very interesting proposal that you can potentially address using near-term quantum device. So there are many motivations, and it's not surprising that there have been a lot of quantum algorithms to prepare the Gibbs state, and this is just some of the existing algorithms. I won't go through all the algorithms here, but today I want to talk about the Gibbs state preparation algorithm based on dissipative dynamics. So I don't know how familiar you are with this Lindblad dynamics or Lindblad equation. So I just give you just a general background. So from physics viewpoint, this can be, for instance, delight. So we consider this kind of situation. There's a system, which is denoted by this blue. And then there's a bath, huge bath, thermal bath. And then there's a weak coupling between them. So this H describes the system Hamiltonian, and H bath describes the bath Hamiltonian. And then there's interaction in between, so this H interaction. So here we suppose that the coupling constant is, for instance, small. Then what you can do is, roughly speaking, you tracing out this bath part, and then you end up with dynamics or system only in a system. And then this interaction is encoded in the dissipation in the system. So this is roughly described by a Lindbladian that depends on Hamiltonian and the inverse temperature that is hidden in this bath, and also a jump or transition or dissipation encoded in this Lindblad or jump operator LA. So this, under certain assumption, this is concisely written in a form of Lindblad equation, which looks like a Schrödinger equation, but now you have Lindbladian instead of Hamiltonian. For example, Lindbladian takes, if you follow the derivation, you will get this kind of Lindbladian. There's the coherent evolution described by Hamiltonian. And then there's a dissipator controlled by this jump operator, as well as the transition parameter gamma A. So this gamma A controls how you, what kind of transition is allowed or not. This equation can be formally solved like a Schrodinger equation. So rho t is given by exponential t Lindbladian applied on rho zero. So this describes the dissipative evolution of the system. So this is the general, well, very brief, but the general description of Lindblad equation. Now, the question that I want to ask, or people have asked from the viewpoint of Gibbs state preparation is, can you engineer the Lindbladian in such a way that its fixed point is Gibbs state? So you want to construct certain Lindbladian that has sigma beta, which is Gibbs state as a fixed point. And of course, on top of that, it has to be efficiently implementable on a quantum device. So that's the target. So of course, you could derive this Lindblad equation, but not necessarily easy to implement. So you want to engineer some Lindbladian that is efficiently implementable. That's our target. So I will show two Lindbladians or generators. When I say generator, it's the same as Lindbladian. The generator of this dissipative vector is Lindbladian in this context. So one is so-called Davis generators, and then I will just raise some nice points about this, and then point out some problem, and then try to fix that. The Davis generator takes this form. So this is a Lindbladian, and a nu is a jump operator, and then gamma is a transition parameter. So now the point of this Davis generator is that a nu a, this nu is energy difference. So you have this jump operator AA, and then this is projected onto certain transition. So that the energy difference before and after the transition is fixed to nu. So you apply projector. This can be written in the form of transform, Fourier transform. So you can also write this way on the right-hand side. So this A nu can induce a transition that has energy difference nu. And then with this nu, you want to apply this gamma transition function. So you want to control this gamma or choose gamma in such a way that this Lindbladian has a Gibbs state as a fixed point. And if you're familiar with, for instance, Metropolis algorithm, you want to choose this gamma in such a way that this accept the transition if the energy is decreasing, and then accept only exponentially small probability if energy is increasing, and so on. So you can play around with this gamma, but at least you want to impose gamma to satisfy this, so that the sigma beta is fixed point on Lindbladian, or in other words, you want to impose this so that this Lindbladian satisfies the detailed balance condition that is sufficient for this Lindbladian to have a Gibbs state as a fixed point. So nice point about this is that by constructing this way, this is exactly detailed balance, meaning that sigma beta is fixed point. However, as you can see from this integral expression, this requires integral of t that goes from minus infinity to infinity. So this comes from the fact that you want to specify nu exactly, kind of with infinite precision. So from the uncertainty relation between time and energy, you have to do the integral of time from minus infinity to infinity. So in practice, this is very costly. Algorithmic viewpoint is this is in practice very high precision because you want to resolve the frequency with very high precision. So that's a problem, but it's nice that this is detailed balance. So this is the Davis generator. Now, there have been a lot of proposals, but I will jump to the recent breakthrough in the quantum algorithm community. That is a different kind of generator, which is called, which are what I call CKG generator. This was proposed by first Chen, Castellano, Brandao, Gillian, and then soon after Chen, Castellano, Gillian, improved this Lindbladian. So the idea is the following: you have Lindbladian. Now, this has very similar form as before, Davis generator. Now, the difference is that this L nu, if you remember A was given by the exact Fourier transform, or you specify nu exactly. Here, you introduce a Gaussian filter in a Fourier transform. So you kind of limit the precision in a frequency domain. And then instead, you are kind of allowed to truncate the interval in T because of this Gaussian filter. So I think it's quite natural. Just by introducing uncertainty in temporal direction that leads to uncertainty in frequency. So it's nice. Now, resolution is finite. But now, if you introduce a truncation in temporal interval, then it seems efficiently implementable. Now, then the problem is that this breaks the detail balance condition. So meaning that by introducing this Gaussian filter, this generator doesn't have Gibbs state as an exact fixed point. So if you try to evolve the system with this Lindbladian, then this eventually goes to some state that is different from Gibbs state. So this is not useful for our purpose. And then what they came up with, this Chen, Castellano, and Villian, is to add some coherent term, G. So in the introductory slide, I had the Hamiltonian of the system here. But here, this G is nothing to do with the Hamiltonian itself. Instead, they designed artificial coherent term in such a way that this Lindbladian has a Gibbs state as a fixed point. So admittedly, this G looks very complicated, but still, this can be implementable in a scalable manner by using efficient quantum circuit. It of course depends on this jump operator and some exponentially decaying function and so on and so forth. It's important that this G1 and G2 are exponentially decaying functions. So even though there's integral of t going from minus infinity to infinity, again, you can truncate this integral. So that's why you can efficiently implement this G. So now it's nice because you don't need the infinite precision or infinity integral in this Lindblad operator. And also they satisfy the detail balance condition, meaning that Gibbs state is a fixed point. So this was a recent discovery that they made. But then, as I briefly mentioned, G still, well, looks a bit intimidating. There's a double integral, and then you have to implement somehow on a device. There's a way, but for instance, if you want to try to implement this on a noisy device, then probably overhead cost, well, not probably, the overhead cost is still prohibitive. So natural question that you would ask is, can we still prepare an accurate Gibbs state even without this G? Can we somehow simplify this part? And then just so you know, the cost of Gibbs state preparation in this context is cost per time step. So you evolve the state under Lindblad version, and then you want to know the cost per time. And then, of course, you want to know the convergence speed, given this Lindbladian, how fast this approaches the fixed point. That's characterized by what is called mixing time. So you want to know the convergence accuracy as well as the mixing time of this Lindblad dynamics. Okay. So now, what is commonly used in the context of physics, especially when the system is chaotic, is what is called the eigenstate normalization hypothesis that models the dynamics or behavior operator in a chaotic system. So we want to adapt this ETH, assuming that the system of interest is chaotic, and then see what we can do to simplify the protocol. And of course, I'm pretty sure that you know a lot of chaotic systems. It's very interesting, and then also it's very hard to simulate, especially real-time dynamics is very hard classically. So it's kind of hope for quantum computing to outperform outperform the classical counterpart. So what is ETH? Just quickly. So given some local orbiter A, and you express this, the matrix element in energy eigenbasis of the system Hamiltonian H, then this is expressed this way on right-hand side. So the first term, this AE encores the thermal expectation value of the system, given some energy E. So here E is the average energy between EI and EJ. What we are more interested in is here the second term. So that is roughly given by random matrix. So roughly speaking, this observable in the energy eigenbasis is described by random matrix theory. But the contribution is exponentially suppressed. So this exponential minus SE over 2, S is the entropy, thermal entropy of the system. And F is a smooth function of E and also energy difference omega. And then finally, this Rij. Here, for instance, in the original Swedenki's proposal, is independent Gaussian variable. So each Rij element. So here I assume that Rij is Hermitian. And each Rij is a zero mean and a univariance, a random variable. So what we are expecting is that given local observable A in a chaotic system, then this A is expected to obey this ETH. So if you this form on the right hand side. Now, the way we adapt this ETH in our protocol or in our simplification or Lindblad engineering is that we assume. So first of all, we take this jump operator that appears, for instance, here A is Hermitian and a local operator. So we choose such operators as jump operators. And then we use this ETH, assuming that the system is chaotic. So we will see numerically how good this argument is. But before that, I want to see how this assumption enters our discussion to simplify the Lindbladian. So this is almost like CKG. So first line is almost like a CKG Lindbladian. Now we don't have coherent term, meaning that this Lindbladian doesn't satisfy detail balance condition exactly, so it cannot be used for Gibbs state equation. Now, what we do, so you just practice the expression of Fourier transform, then you will get the second line. And just to see how this looks like when you use A operator itself. Now, then we want to use ETH. Just remember that this A operator, if this is a local operator Hermitian, then under the ETH, this A behaves like random Gaussian. So the new one is a label for energy transition. So maybe the initial state is I, and then the final state is J, and then the energy difference is U. And then ETH says that this, when you have mu and nu prime, then unless this is the same, under the average of random matrix in ETH, this is vanishing. So it's proportional to delta nu prime. So if you apply ETH and then take an average over this random matrix, then what happens is that this nu one and nu two has to be the same, otherwise they are vanishing. And then same for the second term. So this means that your Lindbladian under this ETH is now looking like this. And then if you remember the form of the first generator that we looked at, this is exactly Davis generator. Meaning that you have nu and nu, and then there's some alpha nu, and so on. And then if you remember, this Davis generator obeys the detail balance condition. So meaning that under ETH, this Lindbladian obeys the linear balance condition. So this has a Gibbs state as an example, Gibbs state as a fixed point. So if this system and then this operator obeys ETH, then actually you expect that this Lindbladian, even though without this ETH, you don't expect this to obey the linear balance condition. Under ETH, this obeys the linear balance condition. So indeed, that's what we see here. So under ETH average, at least Lindbladian now, this is linear balance. And then importantly, this doesn't have coherent term. That was complicated and we didn't want to implement. And then another thing, but I won't go through here as it's a bit complicated, but you can, another assumption ETH also show that mixing time is upper bounded by polynomial of n. So this is done by calculating the spectral gap of Lindbladian. So maybe this is kind of expected if your system is chaotic. Then maybe you would expect the system to summarize fast. And indeed, you can show that mixing time is not too bad, at least not exponential. You can show that this is polynomial in n. So these two are very nice properties, and then we want to see if this works in numerics, for instance. And then, of course, eventually we want to implement it.
So, Yuta, I have a quick question.
Sure.
Did you calculate the gap analytically, or you find the polynomial dependence numerically?
We did both. So we first calculated analytically, but we also did a lot of simplification in analytics. So we also did the numerics to justify that.
I see. Okay.
Yeah. In analytic calculation, it also depends on what's the shape of this f function in the off-diagonal part of ETH and so on. So you need some assumption there. Are there any questions? I think I will now go through some classical numerics, and then after that I will talk about the quantum algorithm. Okay, so first forget about quantum algorithm. We designed some Lindbladian, so we want to see how fast this converges to the fixed point as well as what's the convergence accuracy. So in order to measure the convergence accuracy, we looked at the trace distance between the fixed point or steady state of this Lindbladian and sigma beta, which is Gibbs state. So, and just remember that if you don't, so we take some specific Hamiltonian, and of course you expect that this obeys, well, this shows some property that is predicted from ETH, but still there's a bit some error. So this rho infinity is not necessarily the same as a Gibbs state for some specific instance of Hamiltonian. So we want to quantify what's the distance between this rho infinity, which is fixed point of our engineer Lindbladian and the Gibbs state. Also, we want to know the convergence speed or mixing time. So here it's defined by the minimum time t, such that the distance between this evolved Lindbladian and a steady state is smaller than the mixture. Okay. I will just take our favorite model, simple model. Of course, so this is just one model, 1D6 Ising spin chain. We studied many different parameter sets, but here I show just the one chaotic point. So this plot shows the trace distance in time. So x-axis is the evolution time, and y-axis is the distance between the evolved state and the Gibbs state in trace distance. And you start with we started with maximum mixed state. And then different colors correspond to different number of qubits. So diversion is very costly, even if the system is simple. So we did from 3 qubits to 8 qubits. This is just a classical summation. Now, this dashed vertical line represents the mixing time. So here we took epsilon to be 1%. So when the trace distance becomes 1%, we we read off the time and then we say that this is a mixing time for each evolution. So this is a rough dynamics of trace distance. Now what we can show, for instance, is the mixing time in terms of system size. Admittedly, the system size is not too large, so we want to do a bit bigger experiments or numerical simulation, but this is what we got so far. So x-axis system size, and then y-axis is a mixing time. This kappa, maybe I should explain the different colors first. So here in the Lindbladian, you are free to choose any jump operator. So here we picked the two local Pauli operators as jump operators, and this A, absolute value of A, means a number of jump operators. So for instance, we randomly pick two local Pauli operators, and then that number is 5 for blue. And yellow, this is 20, and then red, this is 50. Generally speaking, as you increase this jump operators, you will express a better convergence. But here, we don't see a lot of difference. I think this is limited by system size. And then this kappa. So we fit this data by mixing time, right, equals to some portion times n to the power of kappa. So the kappa is how this mixing time depends on system size. So here, roughly speaking, for all this number jump operators, we observe polynomial dependence of the mixing time. So kappa is roughly 1.5. So at least for this system, we see indeed the polynomial dependence.
Question about the left plot.
Yeah.
Because you said on the previous slide, this satisfy the I don't know what you call it, the KMS relation, right? You will get in a long time limit, but in this plot, it somehow saturates.
Right. Okay. Right. That's good. So first of all, so in order for the Lindbladian to have the Gibbs state as the exact fixed point, you have to take an average of a random matrix in ETH. And here we choose specific Hamiltonian given by this H. So there should be some distance between the exact fixed point and Gibbs state and this fixed point of this Lindbladian.
So the average over the ETH is actually kind of averaging over the parameters of this Hamiltonian in a small window. Is that the one way to do that?
It could be the case, or of course, ETH average is a bit artificial, so you have to take the average over random Hamiltonians. And then maybe you can do that by randomly picking parameters. I don't know if it's enough to ensure the convergence to the exact fixed point or Gibbs state. But at least there's a statistical fluctuation, and then here we pick just one specific Hamiltonian. That's why we still see the distance.
Sorry, I missed how you do the average. Oh, what you have how to do the average? Okay,
so in this analytical, so in numerics we didn't do any averaging.
Right.
In analytical calculation, for instance, as we see here, we impose this kind of condition using the fact that this random matrix showing up in ETH. So by using this property explicitly.
Mm-hmm.
So for instance, when you want to show that this has a form of Davis generator, you explicitly averaging this jump operator A, and then A is proportional to this random matrix R. So then you can use this kind of property. When you try to calculate the Lindbladian gap, you can do something similar. When you compute the gap, for instance, you have to first take the average over this ETH random matrix. And then also you want to evaluate the fluctuation coming from this random averaging and so on. So in analytical calculation, we assume that this roughly speaking, this A random matrix, and then you can do the calculation.
So in the numerics, you basically are doing the second line on that slide.
Second. So yeah, in numerical analysis, we take this invariant L, right? But then of course we don't actually take random average of A or L. If you pick one specific Hamiltonian or jump operator,
right?
So there's no averaging in the numerics.
Okay.
Yeah. So this distance, for instance, that we see here can be understood as a fluctuation coming from this random matrix calculation, and you can give some bound on this fluctuation as well. Okay. Now, so this was just about the engineered Lindbladian. Didn't show, well, I said that this can be efficiently implementable, but I didn't show how to do that. So here I want to show what's the Lindblad summation algorithm that we propose. This is built upon many recent progresses in the development of Lindblad summation algorithms. So our target is to simulate this guy, exponential TL applied on rho. The Lindbladian is given by this form. By the way, this is the same, roughly same as, sorry, going back and forth, roughly same as this, up to the coherent term. So now there was a transition parameter before we artificially introduced PA. So we just divide the gamma A into gamma and PA. PA plays a role of probability. So you will see what this means. So our protocol goes as follows. And then in the end, we will get this kind of circuit and then we want to break it down. Okay. So first, we sample jump operators. Here we use a label M, so 1 to M jump operators according to the probability PA. Okay, and then you will see why we do this. So PA has a meaning of probability. So if you sum this PA, then this equals to 1. And then we do totalization. So what this means is that, let's say we want to evolve the system for time m delta t, which is equals t, starting from rho 0. Then what we do is first we apply this coherent part given by this early delta t. Ut is given by just a standard Hamiltonian version with some system Hamiltonian h. And then you apply dissipative part. But you don't apply this entire dissipative part, but you only apply one of the dissipative part. And then the label is A1. Where this A1 comes from? This A1 comes from the sampling, jump operator sampling. So every trotta step, so yeah, you could say this way. Every trotta step, you sample one jump operator according to probability PA. And then you apply this peak dissipative version. And then you go to next step, and then you apply the Hamiltonian version. And then again, you pick one random jump operator, and then you go next step and so on. So that's the evolution, kind of randomized evolution. And then next, you want to know how to simulate this dissipative part. So this is very easy. You just add one ancillary qubit. So on top, we have this ancillary qubit, injected ancillary qubit. And then you apply unitary operator given in this form, VA. So now this jump operator is extended by ancillary vector. So this is pure unitary dynamics. And then afterwards, you throw this away and then reset, and then go to next step. So you just use one answering qubit every step. This is called dilation. Turns out that the runtime of this algorithm is beta t mix square over epsilon. So given mixing time, this runs in this within this time if you use this algorithm. So the circuit is again this one. So it's very simple. You do the Hamiltonian summation and then you apply jump operator in the form of unitary. After combining this answer, injected answer qubit and the system qubit, and then afterwards you discard and then reset and so on, and then you repeat this m time. So that's the algorithm. Algorithm itself is very simple. So finally, I just want to talk about noise resilience of this protocol. So this, of course, use information of this quantum circuit. So I just mentioned this at last, but it's very important to simulate this on noisy device. So just to give you an idea, we consider this kind of noise model. So you start with some initial density matrix and then apply the Lindblad dynamics. So we don't need this gamma. So delta t and then L. And then you apply some noise channel. Here for simplicity, we consider global depolarizing noise for the sake of simplicity. So what is global depolarizing noise? Given density matrix, with probability 1 minus lambda, you will get the original density matrix. But with the rest of probability, you will lose all the information. So basically, you get the maximum state. To do some analytical study, we further simplify. So what would you expect this probability? So let's say you have this circuit, patrol tested, and then that contains NG gates, let's say NG 2 qubit gates. Then probability that you will successfully execute this is given by probability that all the gates are successfully executed. That's pessimistic, but that's one way to estimate. So lambda g is the 2 qubit gate error, let's say. Then the probability that none of these are failing, there is the 1 minus lambda g to the power of energy. So that's the probability that you successfully execute this one shorter step. And then for the rest, you will lose all the information. So this is kind of worst case estimate, but this is the one way to model the noise of the system. Now, building upon this this noise model, let's get some intuition how this protocol works. So this green arrow corresponds to one Lindblad evolution. So after one step of Lindblad evolution, if there's no noise, you will get rho t. And the next step, you will get rho 2t. And if mt is larger than mixing time, you expect that this is very close to Gibbs state. So that's how protocol works. However, of course, with certain probability, in this case lambda, you will see some error. So here for simple, let's assume that rho 0 is just a maximum mixed state. We start with a maximum mixed state. And then if there's an error with the probability lambda, you will get the maximum mixed state. But then afterwards, again, if you follow this Lindblad evolution, then eventually you will get the fixed point. The error might happen in the middle of this evolution. For instance, after rho t, you might get some error with probability lambda, and you will go to rho 0. But because dynamics has a fixed point, which is very close to the Gibbs state, eventually this goes to the fixed point. So this is very different from standard unitary dynamics. In case of unitary dynamics, once you see some depolarizing noise, then the fixed point is always maximally mixed state. So whenever you have depolarizing noise or stochastic noise, you would expect that eventually this goes to the trivial state. In that sense, this is the maximum mixed state. But when you are simulating some dynamics that has dissipation and then that has some non-trivial fixed point, then this is not the case. Even though in the middle, your state is disturbed by noise, in the end, there's still the chance that you will get to the target state. This is a simple numerical summation using the information of quantum circuit and then this noise model. So x-axis is just the number of qubits, and the y-axis is, roughly speaking, the distance of between the Gibbs state and the noisy fixed point, divided by the distance between initial state and Gibbs state. So when this is 1, it's quite noisy. When this is close to 0, then it's close to noiseless. There are different colors that corresponds to assumed gate error, 2-qubit gate error, 10 to minus 4, 10 to minus 6, and 10 to minus 8. So lambda G 10 to minus 8 is the most precise hardware, or maybe you need error correction. A different type of curves correspond to, so the solid curve correspond to this Lindblad, noisy Lindblad dynamics. This dashed curve corresponds to some unitary dynamics that has the same number of 2-qubit gates in it. So this just showcases how unitary dynamics is fragile against this kind of noise. On the other hand, Lindblad dynamics is very robust in comparison. And then finally, this dotted line is just analytical upper bound you can calculate, but this upper bound both these curves. So I mean, of course, this if you look at 10 to minus 4 and then going to 20, 40 qubits, then it's even though Lindblad dynamics is better than this corresponding unitary dynamics, but the distance between noisy fixed point and Gibbs state is still very large. But as you increase the precision of this gate error, then of course you expect that Lindblad dynamics shows better performance compared to this unitary dynamics, which is promising. And of course, this is just one example of the dynamics, and then you can choose other Hamiltonian or other simplified dynamics potentially to reduce the error further. So that's about the noise resilience. So I will just go to summary. Okay. So yeah, I think I talked all of this. So I mean, there have been a lot of theoretical proposals, and then on the other hand, there was some numerical summation, but there was still a huge gap between. Well, still there's a huge gap between the theoretical proposals and then numerics, and then also of course hardware implementation. So it's very nice if you could bridge this gap by doing this kind of study. So that was our purpose. Thank you for your attention.
Thank you, Yuta, for the nice talk. Now we can have some questions. Maybe I can start one. Like in the first version of the Lindblad circuit, the jump operator can be written as a time integral. I'm just wondering if you really implement that integral in your circuit, or if one wants to do that on quantum hardware, does one have to implement that time integral in some way? It seems complicated.
Yeah, okay, that's a good point. So I kind of hide that information inside this LA, right? So LA is given by the temporal integral of some Fourier operator with. So this given by Gaussian filtered Fourier transform, and then actually you need to implement the integral. So yeah, you need to. It's slightly costly, but not as bad. So what you do is you simply, so at least we did just discretize and truncate the integral, and then apply this in the form of this exponential. So for example, this LA is now after the truncation and discretization given by sum of this kind of Heisenberg operator of this A, Fourier operator. So you need to apply exponential of those operators sequentially. I don't know how complicated you're imagining. It's not as bad, but you still need to implement that. Yes, it's true.
I see. Yeah. Okay. So the scaling is good, but it's just like some extra work.
Some extra work. We of course constructed the quantum circuit explicitly and did a lot of numerical simulation. So we also know how many gates are required, for instance, in this case. And then it's not too crazy, but yeah, it's still challenging a bit.
I see. And in the approved version where they smear the time integral by adding that Gaussian weight, does that Gaussian weight cause any difficulty in the implementation?
No, I think it's just it just improves the implementability in terms of, well, I mean, so it's just a scalar once you discretize and truncate it. So it just changes the coefficient of each operator at each time step. So it's not bad. Of course, thanks to this Gaussian, you can truncate the integral. You don't have to go crazy truncation parameters. So that's a benefit. And then it's not too crazy. There are, of course, other protocols based on linear combination neutrino and so on. In that case, you somehow have to encode the Gaussian first. But yeah, it's still not too crazy.
Okay.
Yeah.
Okay, good. Thank you.
So it looked like the figure of merit that you used for how closely you prepared the state was this trace distance on the density matrix, and I'm curious, like, what does that mean about so for the actual, like, assuming that rho of t has the form of a thermal state, so e to the minus beta sum h. What are the errors like on the coefficients of like the Hamiltonian that you prepared versus the ones you wanted to prepare?
That's a good question. I think you can bound, but so first of all, the idea of using trace distance is related to the distinguishability of these two states. So operationally speaking, if you can bound the trace distance, then this kind of bound how distinguishable by using the measurement of these two states. So for example, if you want to measure the local operator using this Gibbs state, and then if you know the trace distance between these two density matrices, you can also bound this distance, well, difference between the observable computed from these two density matrices. I think you can read off the coefficients by calculating certain observable set of observables. From there, you can upper bound the distance or difference in parameter of the Hamiltonian, but I cannot answer right now. Yeah, that's a good question. Actually, that's related to the Hamiltonian learning Gibbs thing. So yeah, I think that's an interesting question.
So on your summary slide, you said you are thinking about hardware implementations eventually. I was curious that the last slide that you showed about the amount of error and where would the final role would lie. Yeah, that plot. With the Quantinuum's recent hardwares and the gate errors, where do you think realistically how many number of sites you would be able to do it with reasonable errors?
Very good question. Thank you. So, so if we want to implement this Lindbladian using exactly same setup, at the moment, 2-qubit gate error is roughly 10 to minus 3 to 10 to minus 4.
Okay.
So it corresponds to blue, which looks very bad. So of course we still have to do a lot of things. So one obvious thing that you can do is of course you start with some better initial state. Here we use the maximum mixed state, and says that we don't have any information about the target state. But of course, you could start with some kind of mean field density state or density matrix, or some low energy state you can calculate efficiently and so on. So that makes the mixing time much smaller than what we see here. So that's one hope. Another thing is that, of course, simulating this dynamics for the purpose of Gibbs space preparation may be still hard. But then, as I introduced in the first slide or second slide, there's still a chance of quantum advantage experiment using Gibbs sampling. This is going to a bit the artificial direction because we need to use a random Hamiltonian. But still, you can show some usefulness of the protocol as well as showcasing the performance of this protocol and hardware. And potentially it's hard to classically doing some same task. So there are several different ideas for the hardware implementation. But yeah, if you look at this figure, maybe it's a bit pessimistic. But there are a lot of room for improvement for hardware implementation.
Thank you.
Any other question? Yeah. No more. Let's thank Yuta again.
Thank you.